Now it's time to get back to technical sessions. So I'm Vishal Mishra and I'm chairing this next technical session, which is on data center networks. Again, we have four fantastic papers uh, on different aspects of data center networks. And two of those papers, like the last session, have artifacts available and functional. And the first paper actually even has results reproduced. So that's fantastic for the authors. Thank you very much. And so let's get started. The first paper is designing data center networks using bottleneck structures. This is a collaboration between authors from Reservoir Labs, Yale University, and Columbia University. And the paper is going to be presented by uh, Noah Amsel and Jody Ross Gerald. I hope I managed to somewhat approximate the pronunciation. Noah is a research engineer on the gradient graph team at Reservoir Labs. He works on developing novel algorithms and theoretical models for understanding large networks and optimizing their performance. He joined Reservoir Labs after finishing his BS in CS and math from Yale, where he was researching phylogenetic inference and inductive bias in neural language models. Jody is a fellow at Reservoir Labs. He is a PhD from UCLA. He leads the high performance communication networks team. He's been active in both academia and industry and has developed a large number of technologies that are used in real world products, high performance networking products. More recently, Jody has been working on developing this theory of bottleneck structures, which the next paper is all about, which is the core building block of gradient graph technology at Reservoir Labs. So with that, we'll get started with the paper, and any questions is post on the Slack channel. Thank you.
Hi everyone, I'm Noah Amsel. I'm a research engineer at Reservoir Labs, and I'm here presenting our paper, Designing Data Center Networks Using Bottleneck Structures. So designing data center networks is obviously pretty complicated. In this work, we're taking a formal approach to this problem. So we start from a simple mathematical model of what a network is and how it works, and we build up our theory from there and try to glean some insights from it. So here's our model. A data center network consists of a set of switches and a set of links. Each link has a finite capacity, and we're given a traffic pattern that describes the workload. That is, how much data needs to be transferred between each pair of nodes. We also assume that the network is congestion controlled. This is very important to performance because congestion control is what determines the transmission rates of the flows. And we model congestion control by assuming that it follows the max-min fairness criterion. Now, the goal is to design networks that transmit data efficiently. So the first question we ask is, under our assumptions, how efficient is a given design at transmitting a given traffic pattern? Let's start with a simple example. This network on the left has two nodes shown as gray circles and two links connecting them, both with capacity of 10. There's one flow using each link, one with size 50 and the other 150 bits. So the first flow will finish in 5 seconds, right? 50 divided by 10. But the second flow won't finish for 15 seconds because it carries more data. After 5 seconds, all the capacity of the first link is idle for the rest of the transmission. That seems pretty wasteful. Now look at the design on the right. In this design, the links have different capacities, 5 and 15, but notice that the total capacity is still the same, it's still 20. Now both flows will finish at the same time in this case, so the transmission is complete after only 10 seconds. And no bandwidth is wasted at all, so this design is actually as efficient as possible. As you can see, this design is tailored to the traffic pattern. So the idea is that we want to allocate capacity intelligently so as to minimize waste given what we know about the traffic load of the network. So what makes a design efficient? If you notice in the previous slide, the efficient design both wastes no bandwidth and has a smaller completion time. In the paper, we actually prove that that's true in general. We show that if a design wastes no bandwidth, then its completion time is shorter than any other design that has the same total capacity. So it's optimal in both ways. That's the goal. Now let's see a more interesting, more realistic example. This plot shows a small fat tree topology with 4 hosts. The spine links at the top have capacity of 2. The leaf links at the bottom have capacity of 1. Therefore, this is a full fat tree design. We assume a uniform traffic pattern where all pairs of hosts are sending 1 bit of data. So let's look at how much bandwidth each link can allocate to the flows that use it. The spine links have capacity 2, and they each are used by 4 flows, so they can allocate 1/2 to each flow. The leaf links have capacity 1, and they're each used by 3 flows, so they can allocate 1/3 to each flow, which is less. Thus, all the flows are bottlenecked at the leaf links, and they all transmit at a rate of 1/3. That means that bandwidth is being wasted at the spine links, since each of these flows uses less than the 1/2 that it's given. So now let me pose a question. For the same network topology and the same traffic pattern, how can we alter the design by reallocating some capacity to make it more efficient? So to answer this question, we need a conceptual tool to help us keep track of how congestion control acts on this network. And that tool is the theory of bottleneck structures. A bottleneck structure is a directed graph that models congestion control. For any network, if we're given the capacities of the links and the paths of all the flows, then we can construct a bottleneck structure just like this. Here's how to read this graph. The white vertices are links and the colored vertices are flows. And there's a directed edge from each flow to all the links it traverses. So the blue flow traverses link 1 and 2. And there's a directed edge from each link to each flow that it bottlenecks. So since F3 is bottlenecked at link 1, there's this edge. The slowest flows are the most bottlenecks. They're at the top of the graph. And the fastest flows are at the bottom. So as you can tell, this framework is not specific to studying data center networks or even capacity planning. Really, it applies to any networking problem that interacts with congestion control. Since congestion control is so fundamental to performance, a lot of different problems brush up against it. For example, a lot of problems using traffic engineering or routing can be studied using bottleneck structures. But in this paper, we're applying it to data center networks. So let's return to the question I posed before. How do we make this fat tree more efficient and, if possible, optimal in the sense of not wasting any bandwidth? As before, we have a uniform traffic pattern and capacities of 2 for the spine and 1 for the leaf links. So if we have that, we get the following bottleneck structure. And recall that in this case, we said all the flows are bottlenecked at the leaf links, and that's shown here. As you can see, the spine links are hanging out the bottom of the graph without any bottlenecked flows underneath them. And that indicates that they aren't being fully utilized, and so this design is wasting bandwidth. And in fact, as long as the capacity of the spine links is greater than 4/3 that of the leaf links, you get this same bottleneck structure, and bandwidth is wasted at the spine links. Now let's see what happens if we make the capacity of the spine links much smaller than in the full fat tree. If you get small enough, then the capacity per flow of these spine links becomes smaller than that of the leaf links. So now these 4 interpod flows are bottlenecked at the spine links, and that's shown in the bottleneck structure here. The intrapod flows only use leaf links, and so they're still bottlenecked at those leaf links. Now that every link bottlenecks some flow, it looks like no bandwidth is being wasted. And it isn't at first, but think about what will happen over time. The intrapod flows have the same amount of data to send, but they get a higher rate. So they're going to finish first. And after they finish, the picture looks like this. The interpod flows are still not finished, but now the leaf links are wasting bandwidth. And the bottleneck structure looks like this and evolves the same way anytime the capacity of the spine links is less than 4/3 that of the leaf links. So the last case, of course, is when the capacity of the spine links equals 4/3 that of the leaf links. And in this case, the capacity to flow ratio is the same for all the links, right? 1/3 over 3 is 1/3, and 4/3 over 4 is also 1/3. So now all the links are bottlenecks. All the flows get the same rate, they all finish at the same time, and so no bandwidth is wasted. And this answers the question we posed earlier. For a uniform traffic pattern, this equation says how to design the fat tree to most efficiently use bandwidth. Now let's generalize this question a bit. Instead of a 2-level binary tree, let's consider an arbitrary topology. And instead of all the flows having size 1 bit, let's say intrapod flows transmit sigma bits. So it's a non-uniform traffic pattern. And the optimal design turns out to be what we call the proportional design. A proportional design for a given traffic pattern is one where the capacity of each link is proportional to the total number of bits transmitted by the flows that use the link. So in the last example, the spine links each carry 4/3 as much traffic in total as the leaf links. So we set their capacity to 4/3 that of the leaf links. And in the paper, we prove the following general theorem about proportional designs. If a design wastes no bandwidth for a given traffic pattern, then it's the proportional design for that traffic pattern. So that means if we want to have any hope of being optimal in the sense of wasting no bandwidth, we have to use a proportional design. Now, what about the converse? Can we say that a proportional design always guarantees that we waste no bandwidth? No, not necessarily. The converse isn't true, but it's almost true. We just need an additional condition. So we prove if a design is proportional and the traffic pattern is interference free, then we can be sure it wastes no bandwidth. And interference freeness is a condition on the traffic pattern. For the full definition, you should read the paper. So let's bring this back to fat trees. In the paper, we show that for an n-ary fat tree with L levels and traffic skewness sigma, the proportional design has the following equation. For sigma equals 1 and for sigma greater than 1, the traffic pattern is interference-free, so that proportional design is optimal in the sense of wasting no bandwidth. And for sigma less than 1, the traffic pattern is not interference-free for this topology, and in fact, it's impossible to find a design that doesn't waste any bandwidth. Now let's apply our framework to designing folded clause topologies. The design question is a little different from the one we asked about fat trees because folded clause networks are built out of identical commodity switches. So that means all the links have the same capacity. But there's still a design decision to be made here because it's common to oversubscribe the top layer by removing some of these spine blocks to reduce the cost of building the interconnect. Let's denote the number of spine blocks by beta. In this picture, we have beta equals 2, which in this case is a folded clause with full bisection bandwidth, but you could make beta equals 1, and the picture would look like this. All the hosts are still connected. There's just more flows sharing each link. So the design question that we have is, for a given traffic pattern, how should we set beta to make this network as efficient as possible? As before, we have a parameter sigma that tells us the skewness, right? The ratio between intrapod and interpod flows, and k is the radix of the switches that we're using to build the network. So in this picture, we had a radix of 4 for these switches. Now, if we calculate the proportional design and then solve for beta, this is the equation that we get. Now, obviously, beta has to be a whole number, so we have to round this expression up to an integer. And this formula yields actionable insights for network designers. Let's say we're building a folded clause out of switches that have radix 48. So in that case, the full design would have 24 spine blocks. And let's say our traffic pattern is skewed such that flows within a pod are 10 times larger than flows between different pods. So that means that sigma equals 10 or 1 over sigma equals 1/10. Then this red point here shows us that we only need 20 spine blocks, not the full 24. And if we used more than 20, we'd be wasting bandwidth without improving the time that it takes to finish transmitting the traffic pattern. Now, it's well known that when the traffic pattern is more localized, meaning intrapod is greater than interpod, you can get away with oversubscribing like this. But our model allows us to derive this result mathematically and prove an actual formula that quantifies this relationship. Now I want to tell you about some ongoing work that we've been doing since we finished our paper. We've been working on applying our framework to real-world traffic patterns, like the one from Facebook's data centers that was published recently, and to irregular topologies like the jellyfish randomized topology. In these cases, you can't derive neat formulas like we did before, but you still can predict how the network will behave under our model. This traffic pattern is actually not interference-free, but the proportional design still seems to deliver good performance, right? Most flows still finish at nearly the same time as one another, and the amount of wasted bandwidth is reduced. We can also use our framework to compare different topologies. When using the proportional design and controlling for total capacity, we find that the jellyfish topology wasted less bandwidth and finished the transmission faster than the folded clause and dragonfly topologies did. And actually, a topology's performance seems to be correlated with how interference-free the traffic pattern is for that topology, even though none of them are actually fully 100% interference-free. And this suggests why it might be wise to choose a class of topology that has a lot of path diversity, like a jellyfish, because with the right design, you can squeeze a lot of efficiency out of them. We're building a software tool that implements the mathematical model described in this paper. We've put together some demos that allow you to perform data center design and comparative analysis for HPC interconnects based on our framework. And if you want to play with these ideas, we encourage you to try it out by visiting this URL and let us know what you think. So to conclude, our model allows us to mathematically derive designs for data center interconnects that use bandwidth efficiently. And here's what we're studying next. Initial studies of production traffic patterns that are non-interference free show interesting results. We think we can continue to find new theoretical and experimental results for this case. In the paper, we also assume fixed routing and a fixed traffic pattern. However, we can also use our model as a numerical analysis framework to address arbitrary routing configurations and dynamic traffic patterns. And beyond data center design, the proposed framework can also be used to compose network slices in 5G networks so as to use the resources most efficiently. Thanks so much, and now we'll take questions.
Thank you. I see, yeah, there are two talks, two questions on the talk. The first one is from Nick Sultana. It's a really nice work. The talk seems to equate unused link capacity with wasted bandwidth. But wouldn't you want to leave some slack in link capacity in case of bursts or unforeseen changes in demands within some volume?
Hi guys, and first of all, thank you so much for the introduction, Vishal, and for the question. So yeah, that's a very good question, and I I think in practice, you definitely do want to leave some slack. You don't want to have all the links operating at 100% utilization all the time. The problem, I think, in practice is that there's no necessarily principled way of deciding exactly how much slack you should leave on each link and how to make sure that you're sort of balancing that slack around correctly. So what we hope is that, a designer could start with our design saying, assume that we wanted to use the links at 100% capacity. What would the most efficient allocation of resources look like? And then building on that, they could say, well, now we just want to go, maybe 10% or 20% above that on each link. And it would give them a principled way of over provisioning, well, really like quantitative guidance for how to approach that process. And so, yes, we think we can build that into the model, but you're absolutely right.
Thank you. The second question is by Brighton Godfrey. And the question is interesting work. If I understand correctly, you need to start with a target traffic pattern. Is there a way to use your approach when the traffic pattern is unknown? Or
Yeah,
is there
absolutely
some...
right.
Yeah.
Yeah, that's a very good question. So you're right that we start with the target traffic pattern. And in this work, we only consider cases where you're given a single traffic pattern. What we hope is that in future work, we can address a case just like you say, where we have a range of traffic patterns, or maybe, even traffic patterns that have been sort of sampled from production. And so in that case, you would not necessarily be able to derive the neat equations like we do in this paper, where you can sort of get a formula for the proper design necessarily, but you can still use our model in sort of a numerical simulation to estimate what the best what the best design would be to accommodate a range of different traffic patterns. And actually, if you check out our demo, you can see that idea in action. And we have a demo where, you're able to sort of take in a set of data that's sort of, it's synthetic data that we've used for demonstration, but you can see how you get a whole range of different snapshots, and then you're able to make capacity planning decisions using that data set and sort of simulating the model across time, in addition to just for one traffic pattern. But yeah, very good question as well.
Thank you. And one more question by Nafel Yassin. Hi, great talk. And he wants to know, how do you incorporate failures in the model? Or can you incorporate failures?
Jordy, do you want to take this one?
Sure. So, right. So that's a very good question as well. And the way that, and something that we've also thought about it, but the idea about bottleneck structures is actually you can actually use it for robustness analysis, basically. So you can use bottleneck structures to quantify when a link goes down, what is the ripple effect of that action, and what's going to be the effect on the overall performance of the network, basically. So bottleneck structures, if you look at the paper, allows you to basically compute derivatives very efficiently, and so a link failure is like computing a change on the network, right? So taking the derivative, what happens if that link sort of goes down, capacity goes down to 0, and what's the delta, right? So with that framework, we can actually compute the impact of link failure. We don't do that in the paper today, but certainly we plan to apply bottleneck structure analysis for robustness and analysis in data centers as well. Yeah.
Yeah. So to expand on that, you would maybe we haven't incorporated that into sort of neat equations like the ones that we derive in our paper, but you could have sort of an additional step where you just as like you can imagine trying it on a number of different traffic patterns and trying to find a design that seems to show good performance on all of them, you can imagine trying it on 10 or 100 different failure scenarios, or even trying what would happen if every link, if one of each of the links went down, and evaluate to try to pick a design that succeeds in that case, where in each of those cases you're doing the analysis sort of according to our model. So that's how we would sort of augment it. But yeah, thanks for the question.
I think those are all the questions on Slack. I actually had one question of my own. So you spoke about fixed routing and traffic patterns, which you can expand. My question was about the assumption of congestion control, and you use maximum fairness. How critical is that assumption, and can you work with different other kinds of congestion control, proportional fairness, or some other?
Yeah, that's a very good question. So yeah, at the moment our model is definitely based on this maximum fairness idea. And this is an area that we are definitely planning to explore. But I will say that we have some pilot data where we have shown sort of that the model seems to approximate well enough what the rates look like in real data. So we think it's a model. Obviously, it's not going to be perfect 100% of the time. We think we can get useful insights out of the maximum fairness approach, but we also are hoping to expand this work to other congestion control models as well. So yeah, thank you for the question.
Thank you. So if there are no other questions, I don't see anything, we can move on to the next paper. Thank you
Thanks
again.
so much. Thank you.
Thank you.
Thank you.
So the next paper is titled A Throughput-Centric View of the Performance of Data Center Topologies. The authors are Puria Namiyar Susha from Vidyar Ismedi Institute of Science and Technology, Mingyu Zhang, Minlan Yu from Harvard, and Ramesh Govindan from USC. And the presenter is Puria. And Puria is a third-year PhD student from USC, advised by Ramesh. His research has focused on the design and analysis of data center topologies and in improving the availability and reliability of network systems. Puria has also interned at Microsoft Research to explore related topics this past summer. So let's take it away.
Hello everyone, my name is Puria Namiyar. Today I'm going to present our work on a throughput-centric view of the performance of data center topologies. This is a work with collaborators from USC, WISTEC, and Harvard University. Imagine you are a network designer. Your goal is to provision the network to handle any expected traffic demand. Because if you don't, some traffic might cause congestion, resulting in poor performance for customers. Similarly, cloud providers want their data center network to handle any possible traffic demand. The main reason is that data centers usually work for several years. And during their life cycle, traffic can change significantly. So because it's hard to predict the traffic, ideally cloud providers want their data center to handle any traffic demand. So designing the network to support any feasible traffic demand has some desirable properties. One of them is that you can put your virtual machine anywhere in the network, and the performance of the application is not going to get affected. Such a property can be achieved using a non-blocking topology. A non-blocking topology can handle any feasible traffic demand without causing congestion in the network. Prior work have used a simple metric to determine whether a topology is non-blocking or not. It's called bisection bandwidth. Bisection bandwidth is a simple cut-based metric, and it's equal to the capacity of the min cut that divides the topology into two halves. Intuitively, this min cut should be enough to handle all the traffic demands, including the worst one. And the worst one happens as all the servers on one hand side try to communicate with all the servers on the other side. And since this traffic needs to go through the min cut, the capacity of the min cut should be enough to handle that. This property is called full bisection bandwidth. More formally, a full bisection bandwidth topology has bisection bandwidth at least equal to half of the servers. Any topology with full bisection bandwidth is non-blocking, and this is a property that holds for a class of topologies called CLO. CLO is the family widely deployed in practice. It has this hierarchical structure consisting of a multi-rooted tree. However, CLO is very expensive. If you want to have a full bisection bandwidth CLO, you need to use a lot of switches and many expensive optical links. To address this, prior work has proposed many data center topologies. The most promising ones are expander-based. More specifically, Jellyfish, Expander, and FatClick has been shown to scale well using available switches. These topologies use expander graphs, such as random graphs or cliques, in order to achieve lower cost compared to below, better management properties, and better failure resiliency. Now that we have these elegantly designed expander-based topologies, the question is whether the approach based on bisection bandwidth is useful to check whether these are non-blocking or not. To understand this question, I have to describe another metric to you that has been proposed by prior work, and it's called throughput. Throughput is the fraction of demand the network can sustain. For example, consider this topology in which B wants to send traffic to E at rate 2. But the network can only handle 1.5 rate of traffic. As a result, the fraction of demand or throughput here is 0.75, which is 1.5 divided by 2. Based on this definition, when we say throughput of a traffic matrix is 1, it means that the network can handle the traffic without causing any congestion. Throughput of a topology is the worst case throughput over all the feasible traffic demands. So when we say throughput of a network of a data center is 1, it means that the network can handle all the feasible traffic demands, or in other words, is non-blocking. But the main problem with throughput is that it cannot scale to commercial data center sizes. So up to now, we have these two metrics. One of them is bisection bandwidth, which is scalable, and the other is throughput, which is expensive, but it's very accurate. It turns out that the relation between these two is not very well known. So what we did is we first show that full bisection bandwidth is not equal to full throughput for expanders. More specifically, we theoretically prove for any expander-based topology, independent of the exact structure, there always exists a scale that beyond that scale, no expander-based topology can have full throughput. This number for the state-of-the-art expander-based topologies is between 10 to 15K servers for some parameter choices. So there exist instances of these topologies with only 10 to 15K servers that are not non-blocking, even though they have full bisection. Next, we analyzed cost, management, and failure properties of these expander-based topologies, and we show that when we use the right metric, which is throughput in this case, the results might change significantly, especially at large scale. However, as I mentioned, computing throughput is very expensive. What we did is we proved an accurate upper bound for throughput of expanders and flow topologies that scales to available commercial data center sizes and well beyond that. In the interest of time, I only focus on the first contribution, and for the rest, I refer you to the longer version of the talk. To explain the first finding, I need to describe a fundamental difference between CLO and expanders. CLO has two types of switches. One of them are switches that are not connected to any servers, while the others are switches that are connected to identical number of servers, in this case, 2 servers. However, for expanders, all the switches have identical number of servers, in this case, 2. And this structural difference is what causes expanders to have scaling limitations. So what I want to do is, I want to first show you some scaling results, and then I will explain and give you the intuition for why scaling limitations happen. Here, for one of the expander-based topologies, we show how well they scale while maintaining full throughput compared to full bisection bandwidth. The results also hold for other expander-based topologies, as we show in the paper. So in this plot, the x-axis represents the number of servers per switch, and the y-axis shows the total number of servers. The orange line, or the bisection bandwidth frontier, is the boundary between full bisection bandwidth and less than full bisection bandwidth topologies. And the blue line is the boundary between full throughput and non-full throughput instances of these topologies. More specifically, any topology above the red line doesn't have full bisection bandwidth and doesn't have full throughput. Any topology between these two lines has a full bisection bandwidth, but it doesn't have full throughput. And any topology below the blue line has both full bisection bandwidth and full throughput. As you can see, there exists a huge space between these two lines, consisting of topologies that have full bisection bandwidth but are not non-blocking. The main implication is that when a data center designer wants to employ these types of topologies, they need to be careful about the parameters. For example, let's say you want a data center with 20K servers. If you decide to use 8 servers per switch, your topology is going to be above the blue line, and hence it's blocking. But if you use 6 servers per switch instead, your topology is below the blue line and maintains the full throughput property. But this actually increases the cost because you need to use more switches in order to support the same number of servers. To understand why this scalability issue happens, let me explain 2 types of traffic in a data center. The first one is traffic from or to the servers. For example, when servers under E wants to communicate with other servers, E needs to handle that. The second type is transit traffic that doesn't belong to servers under E, but E needs to use some of its capacity in order to route. For example, flow from F to C that goes through E. Every switch in the network has limited up-facing capacity. For E, it's 3. But E actually needs to use 2 units of its capacity for its servers because it's already connected to 2 servers. And as a result, only 1 unit of capacity is left for transit. The scalability limitation happens as the topology grows, because when we go to larger and larger topology sizes, each switch needs to handle more and more transit traffic. But if you keep the number of servers per switch fixed, then the transit traffic is fixed. Hence, it's a limitation on topology size. What we did is we first showed that in this work that full bisection bandwidth is not equal to full throughput for expanders. And there is a huge gap between these two. Next, we analyzed cost management failure resiliency of these topologies and showed that when you use throughput and when you analyze them at large scale, things can be quite different. For throughput, we prove an accurate upper bound for throughput of expanders and cloud topologies that scales well. Future work can use our throughput upper bound to evaluate practical routing schemes and their efficiency. We can also try to parallelize throughput upper bound computation or try to improve its accuracy. So finally, I want to thank you for giving me this opportunity to present our work. I would be happy to answer any questions. Thank you.
Thank you, Purya. I see questions being typed away, so we'll just wait. Yeah, okay. There's a question by Brighton Godfrey. Thanks for the nice talk. It seems that the statement that expanders can't have full throughput actually is for uniregular expanders, and the limit comes from uniregularity, not from the expander topology. Have you considered how things change when you remove the uniregular restriction? In an expander, it's easy to include some switches that don't have any servers attached, just like in the class network. An expander should get full throughput in that case. Their NSDI 14 paper showed this kind of expander is more throughput efficient than the class-based failed network, for example.
So I think this is a good point, and this is actually a very good question. So I think a short answer to this would be, so the short answer is we haven't analyzed actually what would happen that if we add switches that doesn't contain any servers. But a bottleneck there would be what's the algorithm and how are we going to add those switches that are not connected to servers? And how many of them are necessary for this? I mean, if we can find an efficient algorithm, or I'm not sure if randomization would really help, but if we can find an efficient algorithm, then it definitely would help the cost efficiency and the full throughput property.
Oh, I'm sorry, I got muted. I'm not sure if that answered, Brighton, your question. If I interpret the question correctly, it was whether the results are more because of the uniregular aspect or the expander aspect.
So I think it's because of the uniregular aspect, but it's also because most of the expander-based topologies that we considered were uniregular. So as I mentioned, uniregular topologies, because of those type of transit traffic, cannot scale and while maintaining full throughput. And I believe that adding switches without any servers would help, because then they are not uniregular, or they become biregular. But I think the main challenge there would be how are we going to add those switches that are going to handle the transit traffic, or those switches that are not, that are not attached to any servers. So if we find, I mean, I believe if we do it randomly, then I think it would be a nice question that how many switches that we should add, or, I mean, yeah, that basically the point is, I believe adding the switches would help, but I'm not sure what would be then the head-to-head comparison, like in terms of cost and failure resiliency against Flow. And do we have an efficient way of adding those switches to the expanders?
Okay. Thank you. I see Brighton is typing again, so let's just give him a few seconds while the next speaker gets set up, or the video gets set up. Maybe we could continue that conversation on Slack. You're on the channel, right? The Slack channel.
Yep.
So why don't I think Brighton has a follow-up question, maybe we can respond there. Since we already got delayed with the panel, I'll just move on to the next talk. And
sure.
Thank you once again for the presentation and answering the question. Thank you. So the third talk of the session is titled Congestion Detection and Lossless Networks. Lossless networks, the kind of RDMA networks that have become very popular. This paper is from Tsinghua University. Yiran Zhang, Yifan Lu, Chiang Kai Meng, and Fengyuan Ren. The presenter and the person answering the questions is Yiran Zhang. She's a fourth-year PhD student at Tsinghua, advised by Professor Fengyuan Ren. Her current research interests include data center networks and congestion control. And she'll also be answering the questions. Let's get started.
Hi everyone, I'm Yan Zhang from Tsinghua University. Today I will talk about our paper, Congestion Detection in Lossless Networks. Nowadays, with the advantages of zero packet loss and low latency, lossless network has become an attractive trend in many scenarios, such as high-performance computing, distributed storage system, and cloud data centers. Lossless networks rely on half-by-half flow controls to guarantee zero packet loss under normal operations. Converged in-hand Ethernet employs priority flow control (PFC). InfiniBand develops credit-based flow control (CBFC). In a word, both PFC and CBFC work in the same way to guarantee the drop-free property. The switch ports can alternate between sending and pausing. However, half-by-half flow controls can introduce several side effects, including head-of-line blocking, unfairness, and even deadlock. Therefore, end-to-end congestion control is needed and has received significant attention recently. Among them, congestion detection is the cornerstone of end-to-end congestion control. Now we revisit existing congestion detection mechanism in mainstream lossless networks. Execution is widely adopted in CEE. Execution detects congestion based on queue size. CP max package with ECN according to the RDD algorithm. In InfiniBand, IPCC combines queries information and queue size to detect congestion. If the queue of an output port exceeds a threshold and there are available credits to send packets, the switch port is detected as congested and max package with forward ECN. In lossless networks, when half-by-half flow controls take effect, one problem is that how do they affect congestion detection behaviors at switches? We think this problem has not been well understood. We conduct fine-grained simulations to investigate the interaction issue. We adopt a topology as shown in this figure and adopt execution for CEE, IPCC for InfiniBand. S0, S1, and S2 will all send long-lived flows. A0 to A14 will send concurrent bursts to I1. This burst cannot be controlled by end-to-end congestion controls. First, we set up a single congestion point scenario. At first, F1 and burst start at line rate, so congestion happens at port P3. Then F0 and F2 start with constant 5 Gbps. In this scenario, port P3 is the only congestion point. F1 becomes a congested flow. We focus on the congestion detection behavior at port P2. Port P2 has large unexpected queue buildup due to congestion spreading from the downstream switch. With ECN, some packets of F0 and F2 are mistakenly marked as congested, although F0 and F2 do not contribute to the congestion at port P3. Similarly, in InfiniBand, port P2 also has a large queue buildup due to congestion spreading. Partial packets of F0 and F2 are also mistakenly marked as congested. According to above observations, we draw several insights. First, in CEE, queue-based congestion detection alone is essentially inadequate. With only queue-length information, ECN cannot distinguish between queue buildup caused by congestion and pauses. When the port is on again, ECN checks queue length and may mistakenly mark packets. Second, in InfiniBand, periodical updated queries of CBFC may also confuse congestion detection. The ports affected by CBFC can also receive a few queries periodically. Packets arriving after the arrival of new queries may be perceived to have sufficient queries to send out, resulting in inaccurate detection results. Now, we investigate the interaction issue under the multiple congestion point scenario. Similarly, at first, F1 and burst start at line rate. Congestion happens at port P3. Then F0 and F2 start with constant 25 Gbps. In this scenario, F0 and F2 are also congested. We focus on the comparison between the single congestion point scenario and the multiple congestion point scenario. We take CEE for representation. We find that port P2 has the same queue length evolution and on-off sending patterns during a same period of time. As a result, we conclude that whether congestion happens at a port in an on-off sending pattern may be unknowable. The insight is that the on-off regulation of half-by-half flow controls can mask the real input rate. Once pulses or no queries propagate to the upstream switches, the sending rate of the upstream pulse is regulated to an on-off pattern. Upstream ports will send previously packets at line rate. From the switch wheel, Even the real input rate is different. The incoming traffic is both line rates in a specific time scale. In summary, our detailed observations and analysis reveal that existing congestion detection mechanisms fail to recognize the impact of sending patterns. And a closer observation tells that a pod may have the same equivalence evolution and sending pattern, but the real congestion state is diverse. Based on our observations and insights, we give following definitions of switch pod states in lossless networks. First is non-congestion state. The pod is persistently on and without quick buildup. Second is congestion state. The pod is persistently on. The output rate is at full rate, with quick buildup not caused by off. Third is undetermined state. The output rate is in an off scale, but the cause of quick buildup may be ambitious. In summary, there are ternary pod states in lossless networks: non-congestion, congestion, and undetermined state. Based on our understandings, we propose ternary congestion detection (TCD), which can detect ternary state transitions in switches, and also provides ternary congestion notification to enhance congestion control decisions. The key to congestion detection is to capture state transitions among ternary states. Overall, the state transitions between non-congestion and congestion are the same as in lossy networks. When the pod is continuous on and the coolants exceeds a threshold, the pod is congested. When the pod is continuous on and the coolants is smaller than threshold, the pod becomes uncongested. For non-congestion pod, as soon as the pod enters an off sending pattern, the pod transits to the undetermined state. Next, the transform conditions from the undetermined state to the non-congestion state are twofold. First, the sending pattern changes to a continuous on pattern. Second, because it may take some time for the pod to drain out the accumulated packets caused by off. So if the coolants decreases after releasing from the undetermined state, or the coolants has been already below the threshold, the pod transits to a non-congestion state. Similarly, if the coolants does not decrease after releasing from the undetermined state and coolants is above the threshold, the pod transits from the undetermined state to the congestion state. Finally, a congestion pod can also enter the undetermined state as soon as the sending pattern changes to an on-off scale. According to this state transition diagram, the crucial problem is to distinguish between the continuous on pattern and the on-off sending pattern. Assume the duration of an on period is T on. Our key insight is that a pod in a continuous on sending pattern has an infinite T on, while a pod in an off sending pattern usually has a limited T on. So, in other words, we can seek for max T on to distinguish between these two patterns. We built a conceptual on-off model to describe T on in lossless networks and obtains its upper bound. Please refer to more details in our paper. Last, TCD can support ternary congestion notification. We utilize 2-bit ECN code points, and the TCD performs conditional marking. UE can only be marked when the current code point is not CE. Now we evaluate TCD. The evaluation is mainly composed of the validation of TCD basic properties and case studies. We implement TCD using DBTK and build a compacted topology. We record the marking fraction of flows. For both CE and InfiniBand, the weakening flow F0 is detected as undetermined rather than congested. The validation in the multiple congestion points scenario shows that at port P2, packets are first marked with UE, then marked with CE, because port P2 transits from undetermined state to congested state. Port P1 are in the undetermined state. We also set up a victim scenario in simulations with DCQCN for CE and IPCC for InfiniBand, and use realistic workloads respectively. We record the fraction of F0 flows that are marked with CE. With original ECN and FECN, some flows of F0 are mistakenly marked with CE. With TCD, S0 flows are not mistakenly detected as congested. So how to combine TCD with congestion controls? In general, we recommend congestion controls combining with TCD should perform aggressive rate decrease for congested flows because they are real contributors to congestion, while we should perform gentle rate adjustment for undetermined flows since their real state is uncertain. We recommend to keep the flow rate until it becomes uncongested or congested. In the victim scenario, DCQN combining with TCD has better average flow completion time. With an aggressive rate decrease for congested flows, the congestion spreading can be reduced from the root, and the TCD also avoids throttling unrelated flows mistakenly, so medium and large flows also have faster flow completion time. We also conduct large-scale simulations. For both workloads, DCQN with TCD can reduce the median and 99% FCT slowdown, especially for small and medium flows. To conclude, we understand congestion detection in lossless networks, including ternary part states and their transitions. We propose TCD for CE and InfiniBand. We also show how TCD cooperates with end-to-end congestion controls. We envision that TCD will motivate further exploration of congestion controls considering ternary states. Okay, that's all. Thank you.
Thank you for the very nice presentation, Iran. I'm looking for questions on Slack. So one of the questions that has often come up in discussing these lossless networks that PFC can be problematic, but it's often solved by slide of over provisioning, and you don't actually encounter PFC that much in practice if you over provision a little. Do you have any thoughts on that?
Sorry, can you repeat your question?
Oh, sorry. So the question is that in these lossless networks, if you over provision a little bit, then you don't run into the PFC problem.
Well,
congestion spreading. So
I think actually, I think in today data centers, because there are many short flows and bursty workloads, so you cannot guarantee that PFC is never triggered, I think, because there are always many bursts that you cannot control, and the switch buffer is limited. So actually, I think PFC cannot be avoided totally in RDMA network. It's my opinion.
So is that have you interacted with the operators who run these kind of networks, and what kind of
yes,
PFC triggering they see?
I have some conversations with some operators in industry, and they said actually at first PFC is often triggered, and there it does bring some problem like the congestion spreading and even deadlock. So they choose to only enable PFC at in some of the network, not all the network. And but actually they are also like the no drop property of PFC. So I think whether PFC should be largely deployed is an open question.
Okay, thank you once again. So I don't see any other questions on Slack, but if you have any further questions for the authors, you can always post it on the Slack channel. And the authors can respond in an asynchronous way when they get it.
I will.
Thank you once again for the very nice
Thank you.
presentation. And now we move to the last paper of the session, which is ACC automatic ECN tuning for high-speed data center networks. This is a collaboration between Huawei and Nanjing University, and the presenter for the paper and he'll be answering the questions is Siyu Yan from Huawei Technologies. So let's start with the presentation.
Hello, everyone. Today, my topic is automatic ECN tuning for high-speed data center networks. I'm Siyu Yan from Huawei. I'm so honored to make this presentation. Co-authors come from Huawei and Nanjing University. First of all, as a distributed storage, AI training and HPC applications come up in data center. We can see the more demands for high-performance network. The bandwidth change from 25 to 100 gigabit per second. The future may be 400. The latency become microseconds or less. But the deployment of new high-performance network become challenging. We use an example to explain the problem. When we deploy a new HDMI port, the first thing is to determine the requirement. It needs new feature support on smart NIC or switch chip. The second is set up configuration for runtime, like switch NIC setting, queues, and so on. The third is operating. So considering these challenges, can we make the network operation easier in production DC? So our target becomes clear. From the networking operational point of view, we want to build a smart data plan. Firstly, we hope zero configuration when deploying the network. Secondly, we need to minimize the impact on the tenants at runtime. So we can build up the network by using the default setting of commodity devices and enabling automatic fine-grained parameters tuning over volatile data center traffic without human intervention. DC queuing is the default congestion control mechanism integrated into hardware by most RDMA NIC vendors, and is widely used in DC and work with ECN mechanism. ECN mechanism is supported on commodity switches and affects the DC queuing and network performance a lot. So we can do automatic ECN tuning for high-speed data center networks. When operating the large-scale RDMA network, we see some challenging issues to determine the ECN setting. The first is various traffic patterns demands for adaptive ECN setting. The traffic pattern varies over time. For example, storage OLTP workloads usually appear at daytime. It's delay sensitive, where OLAP is at night or the end of each month, and is throughput sensitive. We build a testbed. In the first case, at the left figure, you can see the optimal ECN threshold is 500 KB for a small queue in buffer with high throughput. But in the right figure, the second case, the optimal ECN is 50 KB. The second observation, we prove and explain the existing solutions of static ECN settings are not adaptive to the variable workloads. In the experiment, we use 3 kinds of ECN settings from papers, as shown in this figure. SECN2 achieves the lowest FCT in left scenario, but SECN1 achieves the best result in the right scenario. Actually, it's because SECN1 is more friendly to latency-sensitive traffic, as SECN2 is for throughput-sensitive traffic. For the SECN0, Lambda and RTT are related to realistic network environment. So it's hard to find appropriate static threshold to balance queue and throughput. The third challenge is operators always struggle to determine the good value for CC parameters. For example, DC queuing mainly has 12 parameters, DC-TCP have 5, HPCC has 3, and Ethernet has 4 parameters, and so on. For these parameters and under the size of traffic demands, it usually takes a few weeks of throughput and latency. Besides, the experienced operators need to have a deep understanding of the application's requirements and network behaviors at high resolution. It's so hard for them. So automatic Ethernet tuning aims, first, it can be adapted to the dynamic traffic. The second is easy to deploy without any modification. The last is good performance with both network and applications levels. To address the above issues with a zero configuration approach, the basic idea is learning-based approach to adjust Ethernet threshold dynamically without human intervention. So tuning Ethernet dynamically can be formulated as reinforcement learning problem. The agent collects data from switches as states and then infer Ethernet actions based on these states. After the agent configures the Ethernet into switch, the agent observes the new states again and get revert to update agent. The agent will gradually be better and more intelligent. When we design it, a straightforward design is that we can apply a centralized DRL agent like a centralized controller to realize the automatic Ethernet tuning. The centralized agent collects the whole network switches states together and infers Ethernet actions for different switch ports. But in the centralized design, the agent has to collect the whole information of topology and the states of all switches, including throughput, queue length, and so on. So there will be a large space of network states and Ethernet actions. The centralized agent will also bring long latency for collecting network states and updating Ethernet configuration. Also, it needs large bandwidth consumption to collect data. To overcome these issues, we introduce a distributed design for dynamic Ethernet tuning at runtime. Each switch has their own DRL agent. Each agent observes the local queue states and chooses an Ethernet action independently. It has some advantages. Dramatically reduce the state action space, reduces transmission latency. Besides, it can avoid the inter-device data transmission. To speed up the training, we apply both offline training and online training. The offline training is to get the pre-training model based on the collected traffic trace. During the online training, the agent interacts with the environment and adapt to the optimized action. For more design details, states represent environment. For example, the network congestion risk. To be compatible with the cloud data centers, they usually contain different vendor switches. We choose the common features supported by major switch chip vendors, such as queue length, output data output rate of Ethernet market, and Ethernet setting. To reduce action space, we discretize Ethernet tuning action space to build the Ethernet configuration templates as switch. We select the key network performance metrics, latency and throughput as a reward function, queue as latency, and link utilization as throughput. ACC can work as a model or container in commodity switch, like white box Sonic. The testbed is two-layer cloud network. It's small-scale pod in the production data center. We test many traffic patterns. The first experiment we use various traffic, exchange numbers of senders and flow every 100 seconds we want to probe. ACC can adapt to the variable traffic. At the same time, we can say ACC have 26% higher throughput and 1 to 3 times lower queue. The second experiment is under realistic applications. The left is under distributed SSD storage system. While OLAP and OLTP are mainly traffic patterns in this distributed storage. ACC can adapt to the different traffic patterns so that it has 10% share of LOPS. The right is under distributed GPU training system. ACC can improve much at training speed with low PFC trigger and latency. We want to see the performance when ACC faces unseen traffic patterns. We generate traffic based on the two realistic workloads, web search and data mining. You can see in the first second, ACC caused a high FCT in short time and quickly converge to achieve a better performance than static ECN. Later, at the time of 8 and 9 seconds, we repeat the old traffic flows again. It's interesting to see because the model has learned the arrival traffic pattern. ACC can quickly adapt to the traffic and get good performance. To show how ACC optimizes the queue occupancy, we sampled the queue length of a switch when a burst of traffic arrives, as shown in this figure. When ACC reacted to the increasing queue length and high link utilization, it used a low ECN threshold to generate more ECN market packs. In contrast, ACC applies a higher ECN threshold to avoid throughput starving. Okay, we have introduced our operational experience for automatic in-network optimization. ECN is the key to achieve low latency, high throughput communications with the state-of-the-art congestion control schemes. We propose ACC, a learning-based approach, which allows automatic ECN parameters tuning at each switch without any modification at any host and ECN protects and switch. ACC has been quickly deployed in the production data center to support storage and computer services. ACC also achieved good performance on both network level measures and application level metrics. That's all. Thank you.
Thank you for a very interesting talk, Siu Yan. So Siu Yan is a senior engineer at Huawei Networks. And he is here along with his co-authors Xiaolong Zhang and Xiaoliang Wang. And he'll be answering questions. So I already see a couple of questions that have come up on Slack. So the first question is by Maria Apostolaki. And the question is very interesting work. Does the correlation between ECN configuration and performance mean that we cannot do unbiased evaluation of different algorithms?
So can you repeat the question again? Right.
So I'll try to interpret the question. So there are congestion control algorithms, and then there's ECN in the switches. So the question is, because the performance depends upon how ECN is being configured, an unbiased comparison of algorithms is not possible without also taking into account how ECN parameters are being set. Do you have any?
Yeah. So from the operating view, so we can say the ECN has a much effect on the performance of the network application levels. So we do this by the learning-based method to adjust the ECN automatically. So if we use the same parameters of ECN in the different various traffic pattern, we can see that from the experiment it has a very low performance. Yeah.
So another way to maybe phrase the question is that some algorithms might be more robust to inaccurate settings of ECN parameters. Do you have any thoughts or comments, or do all congestion control algorithms get affected by ECN?
Yeah, we try to resolve this problem of robust different scenarios. So we do some experiment like we use the aggressive model without any training to face the unseen traffic. So if maybe in the first second it can't quickly converge and the performance maybe is low, but quickly it can learn this traffic and have a good performance. So because in the operating view, we found that the operator always care about the long terms of the performance of the long terms of the benefit of the performance. So this short period low performance, it can't affect the whole application's performance. Yes, so I think this model can adapt to the different scenarios. Yeah.
Okay, thank you.
So, sorry, I'd like to add some comments here. Yeah. I'm the co-author of the work. There are two ways to solve the congestion problem. The one way is we redesign the new type of congestion control, like most of SIGCOMM papers did. That we re-implement a new congestion control at the host or at the NIC, and so which is less sensitive to the parameters at the network, like the ECN settings. That is one ways of solving. And then another is that we can do some improvement at the switches to provide more accurate congestion information to the senders, which needs no modification at the congestion control, or we do not need to modify the NIC, especially in the production line, the production data center that have already deployed at the production data center, and they are using the old NICs that implement the congestion control like DCQC. We cannot modify that behaviors of that NICs. So what our work is doing is try to use a learning-based mechanism to provide more congestion control or feedback information to the host, and try to improve the performance of the system. Okay, that's it.
Okay, thank you. There are a couple more questions. One is by Misha Derry. Thanks for this talk, and want to know if you stop the online training at some point, and when, or do you continue to adjust to new traffic? So does the reinforcement learning keep going on forever, or?
Yeah, when we deploy our ACC, and we keep collecting samples from the at the runtime, and we will but we will keep training our model at the control plane. Like we have a centralized data or samples collecting servers, and which will try to keep collecting the new samples of different application scenarios, and keep training the new model. And after period of time when the when the new model is well trained, we will update the new model at the switches.
So it's a continuous process, or do you stop at some point? I'm not sure if I...
It's a continuous process.
Okay, okay, thank you.
Yeah.
So now the final question on Slack is from Zhou Long Yu. The question is, great work. What's the resource consumption or overhead of ACC? And I think, yeah, maybe you want to decompose it at the switch and the centralized learning mechanism.
Yes, I think Siyu can introduce some details of the resource consumption.
Yes, we compare the resource consumption between the centralized method and the distributed method. I think there some point. One is a bandwidth, another is latency, and the last is the algorithm itself, like the action and action space. At the first bandwidth and the latency, the centralized method is so much, but ACC use a local agent to adjust the incident action. So we only to support the low bandwidth and the low latency. By the PCIe in the switch, it can tolerate this and have a good performance. So yes, that's all.
So I'm sorry, I think maybe I confused the question. The question is, what's the overhead of implementing this on the switches?
Oh, okay.
Overhead of the algorithm itself.
Yeah. The overhead, like some computing.
How much computing power goes to running ACC?
Yes.
In regular switches.
Yes, we need a dedicated core to run the ACC. Yeah.
On every switch.
Actually, I think there always usually has 2 or 4 cores, CPU cores in switch. When we running this model in this switch, it only occupies seems a half of a core or quarter of a core computing in the switch. It's not so much.
Okay. So half to 1 core. That's okay.
Yeah. 20% or 50% of 1 core. Actually, the 4 or more cores in the switch. Yes, it's not so much.
I don't see any more questions. There's a request to put your email address on Slack for further discussion. So if there are more questions, you can answer them on Slack. People can post on Slack. With that, we will conclude this session. Thank you again, everyone, for putting together great talks, for the engaging discussions, question answer sessions. And now we take a break. We have almost caught up with the sessions and panels running longer during the day. So now we originally had a 20-minute break, but now the break is 6 minutes. We'll restart at 2:20 Eastern time. Thank you once again, everyone. Thanks.